Dijkstra algorithm. Okay. As always, we begin with an exercise, and then in between during the lectures, I'll make you do some work. Okay. You must be used to this now. By now, we begin the class with a little bit of exercise, which will wake you up if you're sleeping. It's like a refresher to what we have done last week, right? We talked about graphs and we talked about adjacency matrix, adjacency lists, and things like that. So what I've done here is I juxtaposed two exercises here. One is I have given you a matrix, adjacency matrix, and I'm asking you to draw a directed graph based on this adjacency matrix. So the hint is the graph would be something like this, right, with nodes and edges and all that. And then I say it's a directed graph. You know what a directed graph is? It has direction, arrow. Okay? So here's the matrix. And based on that, I want you to draw a graph. Now, once you finish that one, I hope I gave you the right thing there, yeah. And then I'm saying, okay, I've given you a graph. I'm saying show an adjacency matrix for the graph. Okay? So the second one is opposite with the first one. So there are certain nodes here. 1, 2, 3, 4, 5, right? And then I'm asking you to draw a graph. Okay? Go for it. 5 minutes, 5 to 10 minutes. Okay? By the way, I don't know. I'm just looking at it. I hope I did not give you the answer by that graph. I hope not. We'll find out. Okay? Okay, is the question clear? Take the matrix, draw a graph. Second one, from the graph, show a matrix. Okay, faculty members, please facilitate. Okay, how about we say 7 minutes, okay? Okay, 7 minutes starts now. It's not 12:03 for you there, so until 12:03, 12:04. So until 12:10 to 12:12 you do that. You can turn your video on, so that way I can see the students working. So Shyam Kumar, DNV Shyam Kumar, is from which college? Let me go back to my screen sharing mode here. Give me a second. I see the video of DMS, JNTUV, don't see the video of Jntuk Kakinada today. I'm muting myself. DMS video, you have to adjust a little bit. Tilt the camera angle a little bit so that I can see the students better. How are you guys doing? DMS, you want to tilt your camera a little bit so that I can see your students better. So I only see the heads of the students, not really that they are working at the desk using pen and paper. I can see JNTV, for example, the video, where I can see them working. In your case, I see the faces only, not the desk. If somebody finished problem 1, you can say you finished problem 1. The second one is the adjacency matrix. If you finish that, you can say you finished that. Give me some hint in the chat window that you are done. These are all legitimate exam questions, by the way. So notice the word here, label the notes, right? Okay, DMS completed both. Excellent. That's good. Thank you. We'll wait for one more college to see if they have completed, then we'll move on, okay? DMS is on a roll today. I think they got a little bit of verbal spanking from the student, got a little bit of verbal spanking from me last class. So let me, Jntuk Kakinada completed too. Good. 2 out of 3. I'm sure Jntuk also must be almost done. these exercises to begin the class always serve a dual purpose, right? Number one, it kind of allows them to review what they have learned, kind of make them feel good about it. Number two, for those of them who are still not awake, it wakes them up. And of course, it gives faculty members like me time to go get my cup of tea, right? Even though today I didn't do that. Okay, let me move on then. I have the solution of these somewhere in the slides, okay? So I'll show you the solution in just a couple of minutes. Okay. So here is continuing our review. Completed JNTV, completed 2. Wow. Everyone completed today. Excellent. I think finally you're inspired maybe. Okay. Definition of graphs, right? Graph is a finite set of nodes with edges between the nodes. We use this notation V comma E. V is for vertices and E are for edges. Okay. And then the edges is a subset of V over V, the Cartesian product of that, right? Okay. So that is formal definition. This is how it looks like. So if I give you a set of vertices and if I give you a set of edges, you should be able to draw a graph like that. Okay. So we can say x, y is an edge, and we say x is adjacent to y, and y is adjacent from x. Okay. So that is the adjacency rule. Here is a real life example. I think we covered that last class. I'm not sure. So you have set of people there, and then there is some kind of a relationship, and the relationship that we are showing here is xy, where x is younger than y, then you draw an arrow. Okay? So typically when you are modeling, whether it is database systems, whether it is compilers, state machines, for example, when you do finite state machines, those are nothing but graphs. Okay? Typically, in modeling, you can model people, cities, computers, words, concepts. If you're a behavioral psychologist, then you can start modeling things such as feelings, angry, cool, like a cucumber, right? All the different types of emotions, you can model them too. All of them can form a graph. Okay? In the case, computer networks, right? And of course, you see some other examples, x loves y, x hates y, all that stuff. Okay? So I just basically denote a relationship. Okay? So if I model, if you really look at it, I don't know if you have learned entity relationship diagram, right? When you take your database class, you learn a very great model called entity relationship model. It shows entities and relationships. Concept came out of graph theory. Okay, so you can use it. You pretty much use this concept in every aspect of computer science, and even in real life too. Okay. So we know what the graphs are, and then there are two types of representation, right? We have to represent them, and one we said we'll use adjacency matrix representation. That's what I made you do today. And they have adjacency list representation. Okay. The matrix one you use it when the data is dense, and the list one you use when the data is sparse. Okay. So what are we doing here? Since you completed, you know it, right? Each graph of n nodes is represented by an n by n matrix. Okay, that's nothing but a two-dimensional array. So you label the nodes 1, 2, all the way to n, and then in a given cell in the two-dimensional matrix, you put 1 if there is an edge between I and j. And if it is 0, if you put 0, that means there is no edge. think this is the one that I gave you, I think, right? So I'm assuming that you got, I know all three of you completed. Why don't you respond again saying, did you get a graph like this in the exercise? Who got a graph which shows, I'm showing the graph on the right for the matrix there. You can put yes if you got the graph like this, and you can put no if you didn't get a graph like that. Okay, but I'll move on. You can put your answers while I'm moving on, okay? 0, 1, 0, okay, yeah. Looks pretty okay to me. So this was the second one that I gave you, right? So I gave you the graph on the right and I asked you to build the adjacency matrix. Okay? So you should have gotten something which looks on the left side, which looks like the one on the left side. Okay? We covered these two concepts, so I'll give you an exercise. Okay. Jntuk got it correct. They said yes. DMS and Jntuk we also verify, and you can put your answer yes if you got it. No, you didn't get it. Then of course you have an opportunity to either correct it or defend what you got. Okay. Now, what are the pros and cons, right? When you talk about adjacency matrices, it's a fairly easy concept, two-dimensional array. It's an easy concept to implement, right? And then it's also very easy to tell if a pair of nodes, if there's an edge, right? Right? If there's an edge, there's a 1 in the cell. If there's no edge, it's 0. So it's very fast. It is easier and fast to quickly identify if there's an edge or not. Okay. Now the cons are, of course, you have to have an n by n matrix in memory, right? Because it's an n by n table. And so the moment you have n by n, it's order of n squared. Okay. So that is a con. When you talk about an adjacency list representation, we'll look at some examples one more time. Okay. It is nothing but a one-dimensional array, L of linked lists. Okay. So you have n nodes. To create a one-dimensional array L of linked lists, right? And each Li is a linked list, meaning if you have n nodes, you have n elements, right? And each n element has a linked list, okay, of all the nodes adjacent from the node I. Okay, so if you, and then the second point which is important to note, I don't think I emphasized that last time, I don't recall at least, is this one here. So I have to put that in blue. See, the nodes in the list Li are in no particular order. Okay, just capture them in the linked list. Okay, so how does it look? So it's for the same graph, right? So you have L0 through 5, right? Because we labeled the node 0 through 5. Okay. So L0, okay, empty, and L1 is empty because you are not having any adjacent. Adjacent meaning it's a directed graph, right? There is nothing going out, an out arrow from 0 node and an out arrow from 1 node. Okay. Because it's a directed graph. But if it was an undirected graph, it has things coming in. Okay. I should look at L2. L2 is what John, right? 2 there. So 2 has directed edges going to node 0, node 1, node 4 and node 5 from the graph. So you just list them. It's a linked list. 0, 1, 4, 5. There is no particular order. Okay. Same thing for L3, L4, and L5. Okay. So that is the adjacency list representation. List is a linked list basically. Okay. So that's a slight difference, right? So if I were to an exam question, potential exam question is I can give you the graph on the right, and then I'll say, okay, show me how your adjacency matrix looks like. The one that you have drawn. Okay. And then I can also say, show how an adjacency list would look like. Okay, that is part A of the question. Okay. And then part 2 of the question would be, discuss the pros and cons of each of those two, adjacency matrix and adjacency list. Okay. So when you look at the list, these are the pros. Okay. It saves on space. Okay. Because it only takes as much memory words as there are nodes and edges. Why? Because remember, the moment you say linked list is not static, right? Remember all the concepts that we learned where we do a memory allocation malloc, right? So you use only as much space as required. Where in the case of adjacency matrix, if you have an n by n table, you have to pre-allocate n squared locations. Now the opposite side is it can take up to order of n time to determine if a pair of nodes is an edge. Why? Because you have to search the linked list, right? For any particular I, you have to traverse this linked list. Remember, we learned about linked list traversal. You have to do that, okay? It's going to take time. In the previous case, it was easy to find out if there's an edge or not. All you have to do is go to that cell, array ij, right? The value is either 1 or 0, and then it's order of 1, right? Remember, array indexing, when you do it, we said that in one instance, you can access the array location. Whereas in the case of linked list, you have to traverse the linked list. Okay? So these are like pros and cons like that. We covered this slide. I duplicated the slide here. Yes. Generally, adjacency matrix is good for dense graphs. Okay? Meaning edges are almost approaching the order of V square. Okay? And the lists are good for sparse graphs. Couple of concepts here. In case I did not emphasize it last class, let me put it here. Let me correct this one here. Okay. Okay, this is all not connected. Oh, I didn't want to take that off. Oh. I'm trying to basically group that. You kind of got it right. I did not combine this one. Okay, this is good enough. Okay. So what we are saying here is when we are talking about connectivity in a graph, right? When you have an undirected graph, okay, if it is connected, what you are saying is there is a path between every pair of nodes. Okay, that is a key characteristic of a connected graph. For every pair of nodes, there is a path, every node, right? So if you see on the one on the left, it's a disconnected graph because see the nodes here at the bottom, they are not connected to the rest of the picture. Okay? That's why you call this graph disconnected. Okay? Now, if it is all connected, okay, meaning you can traverse from anywhere to anywhere, there's a path, then we call it a connected graph. So, in an undirected graph which is disconnected, then each piece is called a connected component. Okay? Now, the moment you connect those two, then it is no longer connected because it is one big graph. Okay? That is the second bullet says, right? Now, mathematicians especially are very fond of doing these kinds of things, right? As shown in the third bullet, when you are given an undirected graph G, how do you determine if it is connected or not? You can write a very nice algorithm to find that out, right? Complicated, but you can still write it. Okay? And to make it more challenging, you say if it is not connected, then what are all its connected components, right? How do you determine that? It's a very good computer science problem. Okay, let me pause here. Questions, comments? Still doing good? Not lost yet? Give me a minute. So what we'll do next is in case you're thinking I'm drinking some beer or something like that, don't get me wrong. I'm drinking sparkling water. Okay. I'm one of those old timers where I don't drink alcohol, I don't smoke. So I tell my wife and friends, I'm the most boring guy you will ever find outside of a classroom. Okay. So, there are two standard graph traversals. We kind of did the traversal of trees, binary trees and all that, right? What are the traversal that we talked about in the context of trees? Can somebody put it in the chat? We talked about some traversal of trees. Okay. What are the traversals that we have looked at when we talked about trees? Easy question. You know that because you did exercises too. You forgot? Somebody should know what traversals we learned. Remember the pre-order, in-order, and the post-order traversals in a tree? Right? Those were the traversal techniques that we learned, given a tree. Now, given a graph, in the context of a graph, yeah, there you go, somebody already put it. Thank you, DMS. You're really on a roll today. I'm proud of it. In the case of a graph, when we talk about graph traversals, to begin with, at high level, say depth first and breadth first search. Okay. Do you remember how many of you play chess? Are there people who play chess? Raise your hands if you play chess. Is there anyone who plays chess? So, in the case of chess, right, there's a classic problem. We call it the 8 queens problem. Who knows what 8 queens problem is? You can put it in the chat. For people who play chess, they know that, right? So what is the 8 queens problem? Faculty members, you are welcome to put it in the chat too if you play chess. Do you see any hands getting raised for chess? India is the hotbed of chess in the world now, right? We produce the maximum number of grandmasters now every year. So 8 queens problem, right? The problem is, it says, you have an 8 by 8 board and you are given 8 queens. Your challenge is to place 8 queens on the board, so that way no queen can take the other queen out. Right? Generally, queen can travel horizontally, vertically, and diagonally. So you should place 8 queens such that no queen can capture the other queens. Okay. If you really look at how you go about doing that, I mean, if I were you, I would bring out a chessboard after the class and try to do that. It's a fun game, actually. And in my advanced data structures class, we actually did that. We brought chessboards into the classroom, and we made students do that to teach them a technique. And the technique is called the depth first search. Okay? That is the algorithm that we use to play the 8 queens. Same thing when you play against a computer. If you play chess against a computer, computer is essentially doing depth first search to find the next move. Okay? Before it does a move, it's going to go deep to look at the consequence of that move. And the way it basically builds a tree. It's a graph. Tree is a graph too, right? Okay? Graph can have cycles, trees cannot have cycles. Okay? So it does depth first search. The other one is breadth first search. Okay? So let's look at those two. First of all, the nodes are visited in a very systematic manner, so that way every node is visited exactly once. Remember that. All traversals, even in the case of tree, when we talked about, we said a node can only be visited once. And we used to keep track of the node that we visited, right? Okay. So when you do this breadth first and depth first search, the analysis of that would result in a tree. Okay. So when you visit a node X, it is labeled as visited and it is added to the tree. Okay. Now, if the traversal got to node X from node Y, then Y is viewed as parent of X and X as the child of Y. Some terminology, right? So here are the rules for depth first search. So what are we doing here again? We got a graph. And then we are doing a depth first search. And the way we do that is the following. Okay, there are some steps that you follow in the process of doing depth first search. Step number 1, select an unvisited node X. It could be from anywhere in the exam, because remember, a graph does not have a root. That's another difference. Trees are rooted, right? Now, some faculty member might say, Professor, you are saying only half the story. There's something called free trees. Free trees don't have roots. Okay? We don't get into that level of detail. For the purpose of this class, all trees have root. Okay? So what are we saying here? You select an unvisited node, you visit it, and treat it as a current node. Okay? Now you are going to find an unvisited neighbor of the current node. Then you visit that unvisited node, that neighbor, and make it the new current node. Okay? Now once you are in the new current node, if the new current node has no unvisited neighbors, okay, then you backtrack to the parent. Okay? And then you make that parent the new current node. So repeat steps, actually it should be not 3 and 4, it should be 2 and 3, right? Repeat those steps until no more nodes can be visited. Okay? Now if you still have unvisited nodes, then repeat from step 1. So you have 2 loops going on here. One is the 2-3 loop. And then in step number 5, you're going back to step number 1 and doing that. Okay? Now I'm 100% sure that I lost all of you on this slide, right? If I am a student sitting there like you are, I would be lost too. So what is the remedy for that? It's very easy. I make you do the problem using the algorithm, trace. Remember, we used to do a lot of tracing to understand concepts, right? In the earlier chapters. the same tracing technique comes in very handy here. Okay? So what I want you to do over the next, I don't know whether you'll take 7 minutes. Last exercise you did what, about 7 minutes to 8 minutes. Let's shoot for that, okay? So what I want you to do is, I've given you a graph here. I'm giving you a hands-on exercise to do a depth-first search. Okay? Apply these steps. Now when you do these steps, what are you doing? Remember, you are building a tree. That's what we said, right? And I need to give you a starting point. Okay? So your starting point is node 0. Okay? That is your select an unvisited node X. Your X to begin with is 0. Okay? I want you to do a depth first traversal. Visit all the nodes and show me how the tree looks like. Okay? You're tracing, you're taking this graph and building a tree using these steps 1, 2, 3, 4, 5. You understand the problem? Any questions on what I'm asking you to do? Take your time. I'll give you 10 minutes. Okay? That way you'll also get your 2 or 3 minute stretch break too in that. Okay? In the meantime, I'll definitely go get my cup of tea now. If they're done, then we can move on. I hope you're having fun doing all of these things. Anything to do with graph theory is super exciting to me. In case you're wondering, I'm enjoying a nice cup of ginger tea with a chocolate biscuit. Sorry about that. You can't eat in your classroom, but I can eat while I'm lecturing. Here in our classrooms here, the students are allowed to bring food and eat. For Jntuk, we already put a solution. There's no back to 2, right? Because you have to have, it's a tree. So you cannot have back to 2. How can you have a back to 2? You're visiting every node exactly once. Remember that in a tree. Okay, let's see that. Let's see if someone else also got the same thing or they have got something different. Okay? In a tree, back. Okay, you mean back, I see what you're saying. Traversal, right? And I know what you're doing. Yeah, got it. I understand now what you're saying. Yeah. It actually depends on how your order of traversal to, right? Whether you did a pre-order or a in-order or a post-order to. So there's a little bit traversal concept also involved here. Okay, so let me see if I can go to the next slide. We can always come back to it, okay? It's fun. You have one more exercise like this. So here is the graph and here is the DFS tree. So you said 0, 1, 4, 2, 9, 11, 10, okay? Back to 2, correct? then you did 5, 7, 8, back to 5, then 6. Hey, perfect. JNTV got it right. Amazing. Good job. All of you can clap in your class, right? You did a good job there. Pretty fun, huh? How many students got that in JNTV? There are many groups there, right? Show me hands. How many of you got it right? I'm looking at JNTV picture. You can raise your hand. Show who gave that solution. You can raise your hand. Somebody is raising a hand. Okay, good. Okay. So JNT Kakinada and DMS, if you have completed it, if you got it, you can raise your hand. I can see your video too. Cool. Okay. Practice. Remember, perfect practice makes it perfect. Not just practice. This is all perfect practice for you. Okay, good. Let me then go to the next one. Ready for the next one? Okay. 3, 2, 1, 0. Oh, it's still in DFS. Okay, my bad. So the last node visited is the first node from which you have to proceed. Okay. So the backtracking, if you have noticed one thing, when they said back to 2, that's what they were doing, right? They were backtracking. Okay. So the way it proceeds is last visited, first to backtrack to. Okay. Now the moment you know last visit and first to backtrack to, you should immediately think of push and pop, and that is stack, right? So typically we use a stack to remember the current node and how to backtrack it to. Okay. We learned about stack implementations, remember? So we use those concepts here. So everything is tied. Whatever we learned in class 1 is tied to what we are discussing now, right? I don't know if I'm showing any implementation or not, because that is going into too deep for this class. Okay? Yeah, at least I'm not showing it right now, at least. Let me put it that way. Now let's look at the breadth first search, right? The concept here is instead of going deep, you go horizontally. So you start at level 0 or 1, depending on a reference frame. Then you visit the nodes, right neighbors at the next level, all of them, at a distance of 1. Remember 1 edge equal to 1, right? Then you go visit all the nodes at a distance of 2 and 3 and so on up to the depth of the tree. Okay? So you got these steps 1, 2, 3, 4 there. Okay? Let's see if I give you the same example. Okay? Same thing again, ready, set, go. Right? Here are the steps, here is a graph, and then draw a tree and tell me how it looks like. Again, 5 to 7 minute time frame. I think that sounds reasonable. So we have 2 more classes after today. Just a heads up for you guys. So let me move this one in case I did. We'll wait till at least one group puts the answer in the chat, and then we'll move on. Okay? Faculty members, you can put some feedback from me in the chat in private. If your students are feeling comfortable, you see all of them working and excited, or they feel challenged, whatever feedback you want to put there, you can put there. I do see most of them working though, that's good. All I can say is they seem to be working. If they're drawing some nice pictures of I don't know who the latest heroines are or heroes are. I would not be able to tell from here. Jntuk we completed. Okay. So tell me, what do you have at different levels, right? So let's say the node 0 is at level 0. After one edge, what do you have after at edge 1 or level 1? And like that, you can complete that. Okay? All 3 colleges are doing phenomenally well today. I'm so impressed and I'm actually excited too. That is how I want every class to be, right? Or maybe there's a graph theory that's exciting us all. I don't know if I shared this story with you guys. At UT Austin, when I was doing my graduate studies there, UT Austin, is one of the renowned universities, right? A couple of stories there. One is I actually took a course, Jntuk and I finished to excellent. You can put your answers too, just we'll complete the answers. So I took a course on graph theory from one of the world's, I would say, top 3 graph theorists, Malik, M-A-L-E-K. He's a European, not an Indian. I would rate him as like one of the top 3 teachers with whom I have taken a class. He's done good. But his exams were killers. Here, most of the time, professors give take-home exams. And it's an honor system, right? We don't really worry too much about cheating and all that. I remember on one problem in graph theory, I had to spend 13 hours straight on a weekend. There were about 6 or 7 problems to take home. Finished everything but one problem. I spent 13 hours. And I still could not solve it perfectly. Whatever is the best I could, I gave it. So, later you're saying I came closest to solving it compared to the rest of the class, but I still didn't get it right. So, graph theory is that kind of fun. And 13 hours went away just like 10 minutes, you know. It's so interesting. Good, so you got, some of you got it, so let me go there. So 0, 1, 2, 4, 1, 2, 4. Somebody put 1, 2, 4 at level 1, right? Let me see. So level 0, 0, okay. Level 1, somebody put it as 2 and 1. I think 4 also came in this. You may want to verify that. Somebody put 954. 954. How did you get that? Maybe there are multiple answers, maybe. So 0, the neighbors of 0 are 1, 2, and 4. Okay. So if you go to 2, level 2 is 954. Right, you got it. Yeah, you got it. Level 3 is 11, 6, 7. You got it. Okay. Looks good. Level 4 is 10 and 8. Where is 10 and 8? Oh, because you took 11 as the parent of 10. That's interesting, right? See, what did you prove here? Depending on how you traverse, the nodes can be at different levels, right? Is there one unique answer or can there be multiple answers?
Multiple answers
I could have easily made from 2 to 10, 10 as a neighbor. Then 10 would have been at level 3. But the way Jntuk has done it, they came from the other way around, 2, 9, 11, from 11 to 10. That's why you see level 4, 10. Okay? It depends on how you traversed it. Okay? Good. Glad you got the exercise. So just a little bit more rehash of the same thing with a little bit more detail added there, right? You know the first bullet, I will not repeat, okay? And you implement, typically you implement the breadth first search using a queue. Depth first, we said we use a stack. Breadth first, you are using a queue, okay? There's a little bit of algorithm here, okay? I gave you the steps, slightly different way of showing it, using the perspective of queue, but you can convince yourself once I post the slide deck, okay? Notice one thing here, whenever you're enqueuing, right, to obtain unique traversal, we will enqueue them in an alphabetical order. So depending on the type of traversal and how you want it to be displayed, you can apply certain tricks like that. Okay? So this shows an example of how you traverse this graph here. And the order of traversal, you want it to be A, B. Then you get to D, E, C, okay, G, F, H, I. So whichever way he tried to do that, he built a tree there, okay. A has B, D, and D at level 1. From B, you can go to C, right? So you see C. And from C, you can go to F. And from D, you go to G, and from G to H to I. Okay. And then you have E here. Okay. So you could have easily done from E to G, right? You could have done E, you could have gone to E, and then you could have built the tree from E to G to H to I. Okay? Instead of doing from D, you could have moved GHI underneath E also. And both are correct. However, by doing it like this, that is a trick question, right? So, you can, depending on the type of traversal you want, I say, hey, arrange it in such a tree, that way my in-order traversal would be the following pattern, right? So you should know the pattern also. Okay, great. So most of them, they tend to be like the order of n plus n, again I can convert to n, and then the complexity of an adjacency matrix would be n squared because it's a 2 by 7 by n matrix, right? So the complexity remains the same. Okay. Same thing I give in depth first, where here using the concept of a stack. I'm showing you the concept of a stack here, the pseudocode here. Okay. You can convince yourself as an assignment as to how that works, since we already did some hands-on. Okay. Same thing, I show a stack here. And then you can see you did a pre-order here. We didn't really touch upon pre-order much when we did the tree traversals. We focused on in-order and post-order, if you recall. Okay. There's some code here for those of you who want to see. It is basically like it's an iterative thing you can do here. Okay. So again, I'm not going to touch on the code, go through the details of the code. Okay, 2 pages of code. Okay. Now if you really trace that code, this is a lovely trace. I first thought of deleting this slide, but I thought let me put it anyway to show you how we can trace it very nicely. Beautifully built trace here, right? If you go back to the code, which I skipped, and then trace that code, your picture should look something like this. Okay? Again, you don't need to go to this level of depth in this class, but it is there for those of you who want to know how to write code. Okay? This part of the code, this type of code. Okay, same thing, the code is there. I'll skip that. Okay. If you notice the complexity analysis for depth first search is the same as breadth first search, there is no change. Okay. Now let me stop here for a second because I want to ask a question. The question is this, right? You have depth first search and breadth first search. First question that comes to your mind is, which one I should use when I'm solving problems, when I'm building solutions? I know search is going to be there as part of any problem domain that you do, right? How do you know whether you need to use depth first search or whether you need to write breadth first search? Tough question, huh? It's not an easy question. I really didn't expect any answer from the students here. But faculty members, if there is any faculty member who wants to provide some insight on that, let me know. I'll unmute you and you can talk about it. And if any faculty is there today in JNTUV or DMS or JNTU Kakinada. So I'll give you some answers. These are the type of answers where, unless we go deep, you will not be able to appreciate it. I could have taken an easy route and not even have given you that question to ponder, right? It depends on the data. First and foremost, whether you use a breadth first search or a depth first search, it depends on the type of data and also what is the problem that you're trying to solve. Okay. Google up, it's an interesting exercise for you students. Google up, you say when to use BFS and when to use BFS. Okay, you'll get some very interesting answers on Stack Overflow or Quora, any of these sites, which are the sites where developers go to, right? As they are programming day in and day out, those are the sites that we use. Okay? Because there will always be some expert who is better than I am, but there is no such thing as one programmer knows it all, right? There's always someone better than you. So they write some very interesting answers. One good example that I picked up was, you're all familiar with the genealogy tree, right? The hereditary tree, as we call it, right? So it's a tree, and it's a tree that's obtained from a grass. Okay, the starting node is some grandparent, right? Now you build a tree, and then the leaves. So the tree, the way you look at it, right? Depending on how you build the tree, right? Let's say your goal is to search for ancestors. The current guys are in the top, okay? Meaning the living people are in the top of the tree. And the older guys are at the bottom of the tree, meaning the leaves, okay? If you're looking to find the ancestor, the old guys who died, right? Then depth first is a great technique to get to that, because you're going deep, following. Who is my grandfather? I go from mine to my father to his father, like that. So that kind of connotes a depth first type of a technique. Okay? Backtracking. When you look at all the chess problems, computers, they use depth first search. Similarly, you're familiar with gaming, right? So when you do gaming systems, most of the techniques that you use in gaming software are depth first search. Okay? It's all theoretical right now for you because you don't have practical experience yet, right? You have not taken all the courses. But just giving you a flavor of it. Now, when do you use the breadth first search? Okay? Going back to the an example such as what I'm going to introduce you to next, shortest path. Whenever you want to find the shortest path from one point to other point, when you have multiple in a graph, you have multiple paths from one point to other point. To find the shortest path, we use breadth first search algorithm. Because think about it conceptually, right? I just look at my neighboring points quickly to see which of them is the shorter one. So that way I can take the shorter one. And from there again I look at the shorter ones, right? So that means at every level I'm looking at my adjacent nodes and selecting the minimum of the distance of those nodes. So that is why in the case of the shortest path type of solutions, use the breadth first search. I'll give you another practical example of where we use breadth first search. Let me ask you, how many of you use Facebook? You can raise your hands. I'm looking at Jntuk picture here. Actually, that's a stupid question, right? Who doesn't use Facebook, right? Pretty much everyone uses Facebook, right? So, in Facebook, you have this feature called friend, right? You want to make friends. So, the way the entire friend thing works, you want to quickly identify who the friend of a friend is. Okay? So, you're looking at your list of friends, level 1, then their friends, level 2. So that entire friendship algorithm that Facebook has is based on depth first search. Not depth, sorry. Breadth first search, BFS. Okay? So in applications like that, you use BFS. Okay? Having said that, in reality, generally you brainstorm with your team members, hey, which one makes sense, right? These are the type of things where you want to brainstorm with your team members to make sure you're on the right track before you go deep into implementation, okay? So that much justification I'm giving, no more than that, okay? We get into a lot of other analysis with these two in my advanced class. So maybe I'm doing a marketing for you to enroll in my advanced class, I guess. Okay. Let's talk about some shortest path problems, okay? It's a pretty easy concept. Okay. So multiple paths from a source vertex to a destination vertex. Okay. The path whose total weight is minimum is the shortest path. I mean, since I'm from US, I gave you some, remember one of the graphs was US cities, right? So the guy wants to go from Austin to Washington. There's a path going by Austin, Houston, Atlanta, Washington, which is 1560 miles. Whereas if you go by Dallas, Denver, and Atlanta, the mileage is 2,980. Okay. So you obviously want to take the first one. Okay. Very classic case of finding the shortest path, right? There's so many examples. Same thing, I gave you other examples. Routing messages from source to destination. Again, they use shortest path problem there. Air travel. All these Indian airlines, when they leave in the morning, let's say from Vizag, the nearest airport is Vizag, I believe, right? And from there it has to go to Hyderabad, Bangalore, Chennai, Delhi, somewhere like that, right? Airlines obviously don't want to route the plane which takes more fuel, right? They always want to look for the shortest path. Okay? So that's another practical explanation of shortest path. And the way you do that is each of the edges, here is a graph of the various places or points or nodes, whatever you want to call them. Okay? And you have some weights. Weights could be weight they don't have to be only in miles. It could be time, it could be cost, it could be anything. The weight can have a meaning depending on the problem that you're trying to solve. Okay? And then you calculate the distances from every node to every other node. Okay? So, and then if there's no path, like 0 to 2, there is no path directly, right? That's why you see infinity, meaning there is no path. 0 to 1, it takes 8 quantum, whatever that quantum is. Okay? Like that you have this one. Okay? You have the graph and you have the matrix. From this, you can figure out what is the shortest path. Going from, let's say, from here to what could be the thing? Let's say 2. So if you want to go from 0 to 2, how many paths are there? You have 0 going from node 0 to 3 to 4 to 2. If you add up, that will be 9, 7, 16 plus 117. But you also have a path called 0, 3, 2, which is only 11. That is a shorter path from 0 to 2. Is it? No, probably not. Because you have another path from 0, 1 to 2, which is 9, right? So there should be some algorithm which would let you figure out what the shortest path is from a given point A to a destination point B. Okay? Now, remember I talked to you about Dijkstra? Sorry for the thing here, it's a little bit light, right? Let me see if I can make it dark here. Can I make it dark? Let me check. I think it's like an image, right? I cannot really make this one dark, I guess. Once I upload the slide deck, you can see that. So what Dijkstra's shortest path algorithm basically does is find the minimum cost path between an origin vertex, right, and all other vertices. So he said, first I will build a table which shows all the paths from every vertex to another vertex, what is the shortest path. So that way, when he has to calculate from source to destination, he will use that initial table that he builds to quickly identify the shortest path. So now who is this Dijkstra guy, right? I don't know if I have his picture. I thought I put his picture somewhere, but I could be wrong. Let me check. No, I don't have it. So here's an example of how we built that vertices, the set of vertices. You have all these 0, 1, 2, 3, 4 vertices, and then you calculate the shortest path for each of the vertices in that graph. That's how you fill this table. Okay. And then I'm showing you some illustrations as to find out which path is shorter, right? You have to code it. Typically all computer science students code Dijkstra's algorithm. So right now you're not coding, but I'm just showing you that one. Okay. You're seeing different paths here, the one that I explained to you verbally, and looking at what is the shorter path. Okay. He is basically using that algorithm that I showed in that light blue color one, which you can trace it later after the class is over, right? Okay. So he goes through those steps and identifies all the shortest distances between each pair of nodes. Okay. Then he has this algorithm from step 2 through n, right? So he's going to figure out how to calculate all the weights of all these paths. Okay? And then he takes that figure. Similar thing. Yeah, that's it. We'll continue more. This is only to just set the stage for you for next class, okay? Why is this such a... It is called like one of the... If you look at one of the 10 classic papers in computer science, since the word computer science was coined, this is like in the top 3. Not even top 10, I would call it like one of the top 3 papers. He came up with this algorithm in 1956. Okay. The interesting anecdote about this algorithm, but I'll actually make my students code this algorithm or trace it. Okay. You can expect to do that too in this class. Okay. I'll post some assignment on that. The guy is such a genius, right? I mean, I told you he's already a founding father of computer science. He gave the concept of structured programming. He was one of the founding fathers of giving the notations of structured programming. In the good old days in Fortran, we used to have a thing called go-to statement. Go-to is the antithesis of structured programming. So he basically said we cannot use go-to in a programming language. He was the guy who said that. You're so young, you don't even know what a go-to statement is, okay? But your faculty members should know what I'm talking about. Go-to is a form of arbitrary jump from one place of the code to another place of the code. Okay? Very hard to trace when you have go-tos. In fact, he was so vehement that about go-to, this is a nice story that one of his students shared with us. When the student went to dinner with him at his home, they had their dinner and they were chatting. Then they had to go to Dijkstra's office, study room. He didn't say, let's go to my study room. He said, let's meander, M-E-A-N-D-E-R. He's so against the word go-to, he does not even use the word go-to in real life also, the language. Okay? A lot of great stories because I met him in person in Austin. When Austin decided to become famous in the world, what did they do? They just went and hired Dijkstra from Netherlands for $1 million a year, and next day they became a top 5 computer science department. He is that powerful. Okay? So much for Dijkstra. A lot of great things. You just Google him up, you'll get fantastic stories. He won the Computer Science Nobel Prize. Anyone knows what the computer science equivalent of Nobel Prize is called? You all know Nobel Prize, right? But we computer scientists have an equivalent prize, which is equivalent to the Nobel Prize. It's called the ACM Turing Award. JNTV, you're right, DFS is for minimum spanning tree. We'll be touching on that. Okay. GPS systems, you're absolutely right. Location services, Google location services and all that, right? Nearest restaurant and things like that. We use the BFS. So going back to Dijkstra, he's an amazing character. So he came up with this algorithm. Routers, switches, you name anything, we use that. So next class, I will go just a little bit deep into the shortest path, and then we'll touch upon concepts such as minimum spanning tree, and then there are a couple of algorithms like Prim's algorithm and things like that. I'll touch upon some of those concepts, and then I'll pretty much wrap it up next class. So that in the following class, which is the last class, we'll use it to review all the units. One big sweeping overview of all the units. Okay? Questions, comments? No questions, no comments? Yeah, you did all the work today. I'm very impressed with all the 3 colleges who joined.